So now we're going to talk about chainsaws and avalanche frequency, which is actually pretty appropriate given the past few days and the cycle that just occurred. First, I want to acknowledge my co-authors and folks that helped in the field. Co-authors Dan Fagery, Greg Peterson, Jordi Hendricks, and Carl Berkland, and then Adam Clark and Danny Stelly helped in the field and as well as processing the numerous samples. So, chainsaws and tree rings, what do they have to do with avalanches? I want to try and answer two questions with this. And one is, what's the frequency of large magnitude avalanches in northwest Montana? And what climate variables or atmospheric circulations are contributing to these cycles, or rather these years? So dendrochronology is a study of tree rings, and it can be applied to all sorts of natural phenomena. We chose to study avalanches with it, and I'll show you how we do that. But we can, it's also been used to study things like rockfall, landslides. It can also be used to study climate, looking at the ring width of those, or the width of those tree rings. So what we're trying to do is look at avalanches size D3 or larger, so large magnitude events. So in northwest Montana, basically southern Canada, we went into 4 mountain ranges, and took the chainsaw out for a rip. So we sampled 4 mountain ranges and just under 700 cross sections and cores. It's quite a bit of work to collect this much. Luckily, we were able to use chainsaws, and but still, the processing that takes place when we take these cross sections into the lab, or before we even take them into the lab, is quite a bit of work, and I'll explain that in a little bit. But we looked at it on a spatially diverse landscape here. Again, 4 mountain ranges that, even though they're fairly close together, can experience pretty different patterns and flows depending on what's going on in the atmosphere. So very similar to here, relatively concentrated area, lots of different mountain ranges. Although I think for you guys, they're basically just one big mountain range, but someone decided to name them 17 different names. The Smoky Boulder Tooths. So here's an example of what the terrain looks like. We have John S. Stevens Canyon in the southern part of Glacier Park along the US Highway 2 corridor. And then we have the Going to the Sun Road right through the center of Glacier Park. And so getting back to that map, this is Highway 2 right here. So these are the paths that we sampled in Highway 2. And this is the Going to the Sun Road in the heart of Glacier Park. Here is the Whitefish Range we sampled. This is it's a backcountry area as well as this area in the Swan Range, but heavily used backcountry areas. So we took 2 sort of transportation corridors as well as 2 backcountry areas. So this is what a tree looks like with a scar on it, sort of a cat's face right there, the whole thing. And then the arrow is pointing up, so the uphill direction. Imagine that this tree is now tilted down. Of course, most folks know what this looks like. But this is the impact scar on the tree itself. Let's play this real quick, just an idea of what we do in the field. And where's the little... This right here we suspect could be an avalanche scar. But what we do is then we cut into this dead down tree and then take a thin cross section from this tree. And then we can take that to the lab, process it by sanding it, looking at it under the microscope, counting all the rings, and then cross-dating it. So we had a lot of fun. Who doesn't love chainsaws? Here's an example of a cross-section. You can see this right here is an example of a really big scar. This one from 1972. And to compare that with another scar right here, and this is reaction wood as well. So when an avalanche hits a tree, it oftentimes, if it's a large enough avalanche, it will leave a scar that looks like this in the ring. But sometimes it won't, and it'll just leave a sort of a more subtle signal. And let's use this as an example. So here's a good impact scar from 2003, which is a big region-wide cycle, corroborated with the historical cycle as well, or the observational cycle. And then here's reaction wood from 1959. So what happens is, imagine that we have our tree, and an avalanche hits the uphill side of the tree. If it doesn't leave a scar, like that 2003 scar or something similar, then what could happen if it's maybe not an incredibly large avalanche, but still of decent size, the tree will actually maybe, get hit, but it will buffer, and so it'll grow larger rings on the downhill side to sort of buffer that injury on the uphill side. So you'll see larger rings on the downhill side and potentially thinner rings on the uphill side, but maybe not something as obvious as that scar. So we have, let's see if I have that slide. Yeah, we have 5 different ratings. So class 1 is obvious scar, like that 2003 that we just saw. 2 would be, and reaction would. So, it's all there. All the signals are there. Class 2 might be maybe there's a scar, or maybe it's really thin, hard to see even under the microscope. We have a lot of reaction wood. It's really obvious. You have successive years after that where the tree got hit and, potentially injured, but it's buffering. 3 is, all right, maybe we have some reaction wood, and then the compression wood, which is the really thin rings on the uphill side. 4, it becomes less obvious, and 5 is, well, it's probably a year, but we rate it really, really low. There's just not strong evidence for that. We can distinguish between, or it is possible to distinguish between, other disturbances, but what we did is we sampled in areas where we were not going to have, there are no known landslides or landslide prone areas. There's no rock fall. So we try, because often what can happen is even a moose walking by will hit the tree, and it could actually create a scar. So that's why we look for these other signals like reaction wood and compression wood in successive years. So most of our samples, of course, which is good, were class 1 and 2. So in our over almost 700 samples, we had 2,300 growth disturbances. So that means that we can have multiple disturbances in any given sample. So 2,300 is one of the larger data sets, actually the largest data set so far that's been published at least. So we found disturbances as far back as 1636, our trees went back as far as 1636 up to 2017, but we found disturbances, must be the next one, but found disturbances back to the mid-1600s. So pretty far back. The nice thing about that, let's see if I have it in here. Yeah, the nice thing about that is we don't have an observational record that goes back that far, so we can extend our avalanche chronology pretty far back. The problem, of course, is that far back, we don't have that many trees. There are other disturbances that are getting in the way. Wildfire is often basically erasing all of our potential evidence of trees being able to record avalanches. So you can see that we have more samples, of course, in more recent years. Another reason is that avalanches are basically, again, wiping out the thing that we're trying to study. And so it's sort of this catch-22. How do we get around that? We apply different thresholds to that. Not to make it too complicated, but what we do first is we apply a variable threshold based on the sample size for each individual path. So if a path is, let's say we collected 40 samples from one path, we would apply a certain threshold versus if we collected 100 from another path. So the first threshold we use is the percentage of samples exhibiting a response per the trees alive in that given year, and a minimum number of samples. And again, that varies depending on the sample size. The second threshold we do is a weighted index, which incorporates the signal that I was talking about before, the class 1 to 5. So we weight the class 1 and 2 more heavily than we would, say, the 4 and 5. So when we look at a regional analysis, again, a lot of the work that's been published thus far prior to this has looked at more either single paths or a few paths adjacent to each other. So, we can develop a chronology for any given path, but what we're trying to do here is develop a regional analysis so that we can then associate any sort of climate or atmospheric variables. So it's sensitive to the approach, and what I mean by that is that if we use just this threshold versus this threshold or both, then it's sensitive. The number of resulting avalanche years is sensitive to those thresholds approach. So when you use the weighted index approach, we get 32 avalanche years. And when we use the percentage and the number of responses, so the first threshold that I showed, that's 37 avalanche years. We get 65 avalanche years without using threshold per path, this one, as the first step. So if we don't use that first step, we probably have a lot of noise in there. So there's probably, the trees are telling us that maybe there are more avalanche years than there actually are. So what we did is we it resulted in avalanche years from 1865 to 2017, applying those thresholds. The notable years, of course, are right here. So what we did then is take that with the historical record from the only historical record we have that is of any decent coverage in terms of time is the US Highway 2 historical record. When I presented this in Europe last fall, the person before me had presented, and they were talking about climate and avalanches, and their historical record goes back to, their avalanche record goes back to, I think it was the early 1700s. So that's their observational record. And so I got up there and I was really psyched, and I was like, in our observational record, the really robust stuff goes back to the mid-90s, 1990s. Oh, they laughed. Americans. So when we use our whole record from the mid-1600s, again, this is looking at percent scarred. So just because we have one scarred tree, that doesn't necessarily mean that we have an avalanche. That's why having more data makes a more robust data set. And so that's where the thresholds sort of separate this signal from the noise, so the true avalanche signal from what might just be a moose walking by and hitting the tree. So when we take all of our avalanches, all of our samples from the entire region, we come up with a mean return period of a large magnitude avalanche about every 3 years. Here's what it looks like per path. So this is the central part of Glacier Park. This is the southern part. We only use 2 paths there for this analysis. This is the the Swan Range, the Whitefish Range. And so again, this is showing the median return interval in years. And you can see this path, there's a lot of variability. That path is actually on the eastern side of the Continental Divide. So it has the highest median return period of any. And so we're still working on this part of the analysis, is what's going on between east and west of the divide. When we take all the paths together, we have ourselves roughly our roughly 3-year return period. So when we go to the historical record from the 1990s and onward, wait, I'm not there yet, just kidding. Our notable avalanche years from the tree ring record is all of them had above average snow water equivalent. They all had below average temperatures except for 1 year. And compared to the historical record, it was variable, so they didn't always necessarily match up. And so prior to the 1990s, this is what the observations looked like. Trouble, trouble. Those are the only words to describe the Middle Fork country this past week. Awesome, thanks. That really helps. So this is looking at snow water equivalent. 19 of our 27 years had an average or above, and there was a significant difference between non-avalanche years and our avalanche years from the tree ring record. You can see here, this is our SWE mean, and you can see that the avalanche years are in red triangles, and again, most of them are above. Now, as we all know, we're talking about annual SWE amounts here. And avalanches, of course, depend on weather. Climate drives that weather. But we could have a low snow year, but if it's a weak snowpack structure, for instance, any given storm could easily cause a large magnitude avalanche. So that's why, as you can see, we still have years of below average SWE where we do get large magnitude avalanches. So what we did is we took a bunch of variables, basically used a technique called principal component analysis, and we took these variables. Basically, it's like a salad bowl. You throw them all in and see what teases to the top. And we found that our first component in describing or in identifying the variability of our avalanche years was El Nino Southern Oscillation and Pacific Decadal Oscillation. So the interaction of ENSO and PDO explain about 42% of our variability, which is actually pretty good. The second component was snow depth and max temperature, and that explained about 13% of our variability of those avalanche years. So over half of our variability can be explained by atmospheric circulations, snow depth, and maximum winter temperatures. And you're thinking, well, of course, it's called a storm. And so, but in terms of a long-term climate, our next step is trying to identify any trends. So what we're seeing here and what we found so far is a negative PDO and a negative El Nino, also known as a La Nina, what happens in the Pacific Northwest is we get a prominent low pressure due to cool sea surface temperatures in the North Pacific. And again, this is that interaction between PDO and ENSO. That results in above average snow water equivalent anomalies here. Again, this is where we are in Northwest Montana. So in terms of spatial analysis, we can also use this work to look at avalanche return periods across the landscape. So here's an example where this is the railway, this is a snow shed, this is the top of the avalanche path that's actually up here, and then this is the run-out zone, and the road, Highway 2, is down here. So what we do is we take our individual samples from each individual tree, and then we extrapolate that across the landscape. And there are a variety of ways to do this, kriging or inverse distance weighting. And you can see that we can actually create return period maps for any given avalanche path. The problem with using some of those techniques in just sort of extrapolating across a generic polygon on the landscape is that you can often have artifacts like this. This is another path in the central part of Glacier Park. This is the starting zone way up here. You can see there's the lower return period, and then all the way down here there's a much higher return period. I masked out the 1967 fire because, again, another disturbance that could potentially affect our samples or the availability of our samples. So this is, again, what it looks like if we sort of just take a generic polygon and plop it down on a landscape. But when we tailor it and we use sort of expert knowledge of what the avalanche paths actually look like and how we sort of use historical data of where most of these avalanches occur, because maybe there's a flow in the landscape that we just can't quite identify. And that allows us then to say, well, no, this area really doesn't get hit. So we then apply, again, an expert knowledge to this and create our own polygon. And we were able to come up with more realistic return periods across these avalanche paths. So our return intervals for our areas are roughly every 3 to 4 years. Our atmospheric connections are characterized by above average snow water equivalent and snow depth. Pacific decadal oscillation and La Nina, and negative PDO and La Nina. Snow depth and max winter temperatures are influential in our large magnitude avalanche years. But again, caution inferring any sort of climate signal with avalanche phenomenon and climate change. And so that's sort of our next step, is to look at a trend analysis with a longer record. So what we're going to do is take reconstructed snow water equivalent from tree rings, so just using tree rings to sort of look at climate. And that record allows it, or goes way further back. So we're then going to use that climate record and our record that goes back to the 1600s and 1800s with our avalanche record and compare the two and see what we have. Because of course our SWE and snow depth only go back to the 1930s, at least in this area, is only what we have for SWE and snow depth. And then trying to determine what does regional actually mean. Is this representative? Is using 4 mountain ranges and the number of samples that we collected representative for any given area or even this area? So I think we're going to try and do a little bit more of this work. We're doing a bit of as well in Juneau this summer, and then heading down to Colorado as well to try and collect some samples after the historic cycle there in March. And then we were able to collect 1 sample yesterday on our way out. It's actually kind of cool because you could see one of the scars. What was the path called? Or we were in Beaver Creek. So we collected a sample there by hand. We didn't use a chainsaw. And found that, at least, looking at it, not even under the microscope, is probably roughly a 40-year return period, maybe, all the way down there by where the road crosses, we think. So, yeah, if you have any questions, let me know. Thanks.